Reactions often occur by a series of elementary steps, and when this is true, the overall experimentally determined orders will reflect all of those steps. In addition, the experimentally determined rate constant is typically a combination of elementary rate constants. So the experimentally determined rate law contains information about the mechanism. Let's see how we can back out information about the mechanism of the reaction by simply determining the rate law for the reaction experimentally. The typical way to approach this problem is in reverse, much like you would do a retrosynthesis in organic chemistry. What we'll do is propose a mechanism and then see what rate law would be predicted by that mechanism and see if it matches the rate law that we measured experimentally. If the proposed mechanism predicts the experimental rate law, then that mechanism is a likely mechanism for the reaction. It is not the only mechanism that might predict the correct rate law, and therefore we never can say that a mechanism is for certain. We cannot prove that a reaction goes by a certain mechanism. We can only say that that mechanism is plausible and fits experimental data. As an example of the types of reactions that go into mechanisms, let's take a look at the accepted mechanism for the enzyme catalyzed conversion of a substrate to a product. Most mechanisms can be broken down into three different types of reactions. Opposing reactions, or equilibrium reactions, in which the forward reaction and the reverse reaction are important. Consecutive reactions, in which an intermediate is made in one reaction and then used up in a following reaction. The third type of reaction is illustrated when we have an inhibitor in addition to the substrate. This is a parallel reaction in which one reactant is used up by two separate reactions to form a product or an intermediate. So the enzyme is used up either by substrate or inhibitor to make an enzyme substrate complex or an enzyme inhibitor complex. This is an example of a parallel reaction. Note that in the case of the simple enzyme substrate mechanism with no inhibitor, the net reaction is that substrate becomes product. Recall also that we can write the rate law for the elementary steps simply by looking at the stoichiometry of each of the elementary steps, since these steps depict what is actually happening on a molecular level. So for instance, if I want to write the rate of appearance of product in time for this simple enzyme mechanism, I look for the reaction in which product plays a role. The only reaction in which product appears is the second reaction, and so I can write that that rate is a rate constant, we'll call that K2 because it's the second reaction, times the concentration of the reactants. On the other hand, if I want to write the rate of disappearance of the substrate, I must include not only the rate of disappearance of the substrate from the forward reaction, we'll call that rate constant K1, times the concentration of reactants, but also the rate of appearance of the substrate by the reverse reaction. And so we have to add in that substrate appears according to K minus 1 for the reverse reaction times its concentration of reactants. Notice that the enzyme substrate complex are the reactants for the reverse reaction. In the case of the parallel reaction, if I want to write the rate of appearance or disappearance of the enzyme, let's look at the disappearance of the enzyme. I will write K1 E times S minus K minus 1 for the reverse reaction times the enzyme substrate complex concentration, plus the enzyme also disappears when it reacts with the inhibitor, so plus K2 times E times the concentration of inhibitor minus K minus 2 times the concentration of the enzyme inhibitor complex. Notice that our rate equation for the disappearance of any of the components in our mechanism will include a term for each reaction in which that component appears. So the enzyme appears in 1, 2, 3, 4 reactions, and so I have 4 terms in my rate equation. In each case, the rate law that we obtain from the mechanism cannot be directly compared to the rate law that we determine experimentally. First, these include the concentrations of intermediates, which are often difficult to measure or impossible to measure, and our experimental rate laws do not include the concentrations of intermediates. Furthermore, these rate laws from the mechanisms are often sums of rate laws for elementary steps, whereas the rate law that we determine experimentally typically does not include a sum and is a simple power law. Luckily, as we will see, we can use stoichiometry to reduce these rate laws into a simpler form. In addition, we can make several approximations which allow us to write these rate laws in a simplified form which can be compared to experimental data.